EDX Decision 1, Linear Programming, Formulation and Graphical Solutions. Graphical solution when the integer solution is required. Once we've plotted the constraints, we can solve using the graph. We've already seen the vertex method and the use of the objective line to find the optimum solution. So far, we've assumed that our variables x and y can take on any values within the constraints. However, you will get some questions where we need an integer solution to the problem. So only the specific points in the unshaded region represent valid solutions. So we can only have where the crosses are as valid solutions. Notice, because the constraints include equality, we can have integer solutions that are on the lines as well in this case. So these are the only possible integer solutions that we need to check. So here we're trying to maximize p equals 3x plus 4y, and we need an integer solution. When we used our vertex method and our objective line, we got the solution b, which is at 2, 3. So in b is 2, 3. P max was 3 times the x coordinate and 4 times the y coordinate. P max was 18. So that was when x was 2 and y was 3. And we can see clearly that x and y were integer solutions, and therefore that is still the optimum solution. However, when we look at the minimizing problem, when we use the tour of vertices method and the objective line, we got the solution which was at E, which was 15 over 23, comma 40 over 23. Now clearly that is not an integer solution. So we need to check for the integer points close to that vertex. So I'd definitely be checking that point. And I'd be checking that point, and I'd be checking that one. Remember, we're looking for a minimum solution. So if we call them RST, so we've got R, which is the point 1, 2, and P would be 3 times the x coordinate, so that's 3, 4 times the y coordinate, so that would give us 11. We've got S, which is the point 2, 2, so P is 3 times the x coordinate is 6, 4 times the y coordinate is 8, gives me 14, and I would also be checking T, which is the point 3, 1. So P there, 3 times the x coordinate, 4 times the y coordinate, and we can see the minimum solution is 11, which is the vertex near to E, but there's no harm in checking the others, but it should be the vertex near E. So our optimum solution here would be P is 11, and that happens when we have integer solutions x equals 1, y equals 2. So in this example, the feasible region is unshaded, the vertices coordinates have been given a, b, c, d, and the objective function is to maximize p equals x plus 3y. So I've drawn an example of an objective function nice and clearly. I'm going to use this objective line to find my maximum vertex. So the 3 things we're going to do is 1, find the optimum vertex, 2, what's the maximum value of p, and 3, if x and y need to be integer solutions, what would be the optimum point and corresponding value of p. So using this objective line, I've found the solution is B, so the optimum vertex in this example is going to be B, so that's 1.53. The maximum value of P using the objective function is P equals the x coordinate plus 3 times the y coordinate, so that's 3 3s are 9, so that gives me 10.5. And that will happen, remember, when x is 1.5 and y is 3. However, we now need x and y to be integer solutions. So the points we need to be checking are the points 1, 2. There's an integer solution. I'd also be checking 2, 2 and 3, 2. So let's look at those points. So at the point 1, 2, that's an integer solution close to B. I would get P equals, we need x plus 3y, so that's 1 plus 6 is 7. At the point 2, 2, we get P again is x plus 3y, so that's 2 plus 6 is 8. And lastly at the point 3, 2, we get P is x plus 3y, so that's 3 plus 6 is 9. And it's quite interesting here that our optimum integer solution is here, which is quite a long way from B, but needed to be tested. Don't assume that it's always going to be the closest one to B. So here the best solution on the graph is quite a distance from B. So our optimum integer solution is P is 9, and that occurs when x is integer 3 and y is integer 2. And that brings us to the end of formulation and graphical solutions.